What's up everyone, it's Stack Lessons here. Welcome back to the channel. Today we're diving into Amazon Athena, serverless querying and cost optimization. Let's get into it. By the end of this video, you'll know the exact 7 knobs that turn a $5 Athena query into a 50-cent query. And Athena cost optimization is one of the highest frequency topics on the Amazon Web Services Certified Data Engineer Associate exam. Here's the uncomfortable truth most candidates miss. Every Athena exam question, no matter how it's worded, is really asking the same thing: how do you query faster and cheaper? Get that lens right, and a whole domain of questions becomes obvious. Look at that, same logical data, same query, same Athena service. 1 terabyte of raw CSV costs you $5 to scan. Convert it to Parquet and the same query costs 50 cents. That's a 10 times reduction from changing one thing, the file format. And here's the kicker. The Parquet version actually runs faster too. This single comparison drives almost every Athena answer on the exam. So what is Athena really? At its core, Athena is a serverless SQL engine built on open source Trino, which was forked from Presto, itself created at Facebook, by some of Presto's original engineers after they left Meta. Athena Engine version 3 runs on Trino under the hood. You point it at S3, and you run standard SQL, no clusters, no nodes, no provisioning. Athena uses the Glue data catalog as its metastore. That's Amazon Web Services' central metadata store for tables and schemas. That's important because the same catalog is shared with Redshift Spectrum and EMR, so one table definition serves multiple query engines. The pricing model is brutally simple: $5 per terabyte of data scanned. That's it, no hourly charges, no per query fees. And if nobody runs a query today, your Athena bill is literally zero. You only pay the Glue catalog and S3 storage underneath. Here's the mental model that unlocks every Athena question. Athena is a taxi that charges by the mile, not by the trip. A wide, scenic route like Select Star from a huge CSV costs a fortune. A direct shortcut, pick 3 columns from Parquet with a partition filter, is dirt cheap. Every single optimization technique we're about to cover is just a different way of shrinking the bytes scanned. That's the whole game. Picture this: a CSV file is a paper phone book. To find everyone in Ohio, you have to read every single line, every column, top to bottom. That's row-based storage. Pick a single column from a CSV, and Athena still reads every byte of every row. 1 terabyte scanned, $5. Parquet is the opposite. It's a phone book organized by column with a state tab index. Need just the state column? Flip directly there. Skip the other 49 columns entirely. And because each column compresses independently, typically with Snappy or gzip, that same logical terabyte often shrinks to around 100 gigabytes on disk. One quick gotcha: when you write Parquet with a CTAS query in Athena, the default compression is actually gzip, not Snappy. If you want Snappy, you have to specify it explicitly with Parquet_compression equals Snappy. Same data, 50 cents. The exam loves this triad: Parquet plus partitioning plus compression. Memorize it. Let's see this in numbers. Same 1 terabyte of logical data, 4 different storage strategies. Raw CSV, the baseline $5 a query. Gzip that same CSV, and you're down to about $1.50 because Athena scans the compressed size. Convert to Parquet with Snappy and you're at 50 cents. Now add smart partitioning plus partition projection and you're at 5 cents. 100 times cheaper than the original. None of these steps required spinning up a single EC2 instance. This is just file format and layout decisions. The second cost lever is partitioning. You organize your S3 data into folder hierarchies: year equals 2024, month equals 11, and Athena skips entire prefixes that don't match your where clause. In this diagram, the query filters for November 2024. Athena ignores 2022 and 2023 entirely. Inside 2024, it ignores October and December. It only reads the files under year equals 2024, month equals 11. But here's the trap exam writers love. Never partition on a high cardinality column like user_ID. You'll create millions of tiny folders, each holding a few rows, and Athena's S3 list overhead will tank your performance. Partition on low cardinality columns date, region, event type, where each partition holds a reasonable chunk of data. Partitioning is great, but it comes with a hidden tax. Every time new data lands in a new partition folder, somebody has to tell the glue catalog that the partition exists. The traditional way is to run a command called MSCK REPAIR TABLE, which walks S3 looking for new folders and registers each one. On a small table, fine. On a table with hundreds of thousands of partitions, think VPC flow logs over 3 years, MSCK REPAIR can take over an hour to run. And you have to run it every time new data arrives. This is operational pain at scale, and the exam knows it. Here's the analogy that makes partition projection click. On the left, MSCK REPAIR is like manually updating the table of contents of a book every time a new chapter is added. Someone has to walk through the whole library, find new chapters, and write each one into the index. Slow, manual, error-prone. On the right, partition projection is printing the formula on the cover of the book. Chapters are numbered 1 through N, 1 per day, starting January 1st, 2020. The reader calculates which chapter to flip to without anyone ever updating an index. That's the difference between catalog state and runtime computation. Athena reads the partition formula from table properties and figures out the S3 locations on the fly. No MSCK REPAIR, no alter table ADD partition ever. Straight from the Athena user guide. Partition projection eliminates the need to add partitions manually. Athena calculates partition values and locations using configuration that you set on the table, rather than reading them from a metadata repository. Read that twice. The key phrase is calculates rather than reads. No catalog lookup, no maintenance command, no scheduled job to register partitions. If you see any of those pain points described in an exam scenario, pick partition projection. Here's what partition projection actually looks like for Nexar Retail's VPC flow logs. The crucial part is the table properties block at the bottom. Projection.enabled equals true switches the feature on. Projection.dt.type equals date tells Athena this partition is a date. Projection.dt.range gives the formula start at January 1st, 2020, run through now, which auto-updates. And storage.location.template tells Athena how to build the S3 path from a partition value. From the moment this table exists, new daily folders are queryable immediately. No MSCK REPAIR. No glue crawler runs. The formula is the catalog. Projection supports exactly 4 types: enum, integer, date, and injected, covering basically every real-world partitioning scheme. Next cost lever CTAS, which stands for Create Table As Select. From the official Athena docs. A Create Table As Select query creates a new table in Athena from the results of a select statement from another query. CTAS queries are useful for transforming data that you want to query regularly. What's important here is the use case. CTAS is the cheapest way to convert raw CSV or JSON data that's already in S3 into Columnar Parquet format. No glue ETL job, no EMR cluster, no Spark code, just one SQL statement. Here's a complete CTAS for Nexar Retail. We're taking the raw sales CSV table and writing it back to S3 as Parquet with snappy compression, partitioned by year and month. The format property says Parquet. The Parquet _ compression property says snappy, the exam favorite combo. The partitioned _ by clause lays out the year and month folders. An external _ location is the S3 prefix where the new Parquet files land. Then the select at the bottom feeds in the source data. Run this once, and Nexer Retail's sales data is now in columnar form, partitioned, compressed, and ready for cheap queries. This is the answer when the exam asks, what's the cheapest way to convert CSV already in S3 into Parquet? One critical gotcha. A single CTAS statement can write at most 100 partitions in one shot. If you're converting 3 years of daily partition data, that's over 1,000 partitions, and a naive CTAS will fail. The fix is to do a small CTAS first to create the table structure, then use insert into statements in batches, say, 1 year at a time. Or use the bucketed _ by clause instead of partitioning if the cardinality is too high. Exam writers love this limit because it's an easy distractor. Now imagine Nexer Retail has 3 teams sharing Athena, finance, marketing, and data science. Without workgroups, all their queries pile into one query history, one results bucket with no cost controls. Chaos. Workgroups fix this. Think of them as separate office floors in the same building. Finance gets their own conference rooms, their own supply cabinet, their own security badge, and a credit card spending limit. Marketing gets the same isolation with different settings. Data science too. In Athena terms, each workgroup has its own S3 results bucket, its own encryption configuration. Marketing uses SSE-S3, while finance and data science use SSE-KMS, its own CloudWatch metrics, and crucially its own per-query byte scanned cutoff. Finance is capped at 100 gigabytes per query. Marketing at 10. Data science needs to run big machine learning jobs so they get up to a terabyte. 1 Athena service, 3 completely isolated team environments. Amazon Web Services sums it up in one sentence. You can use workgroups to separate users, teams, applications, or workloads, to set limits on the amount of data each query or the entire workgroup can process, and to track costs. Notice 3 things packed into that sentence: separation, limits, and cost tracking. Any exam question that mentions even one of those words, especially in combination, is pointing at workgroups. If you remember one workgroup setting for the exam, make it this one: BytesScannedCutoffPerQuery. It's a hard limit set per workgroup that cancels any query once its scanned bytes exceed your threshold during execution. 1 junior analyst types select star from a 100 terabyte log table by accident. Without the cutoff, that's a $500 query. With a cutoff of, say, 10 gigabytes, Athena cancels it once scanned bytes cross the line, and note that the data scanned up to that point is still billed. This is the answer whenever the exam mentions preventing runaway costs or limiting accidental full table scans. Up next, Athena Federated Query. Picture this. Nexer Retail's order status sits in DynamoDB, Amazon Web Services' fast key-value database because the website needs sub-millisecond lookups. Historical orders are in S3 Parquet for analytics. Customer profiles are in RDS Postgres. Without Federated Query, you'd build a nightly ETL pipeline to dump everything into one place. With Federated Query, Athena dispatches Lambda-based connectors, one per data source, that translate Athena's SQL into each system's native query language. The DynamoDB connector speaks key value. The RDS connector speaks Postgres. The Redshift connector speaks Redshift's dialect. S3 stays the native path through the glue catalog. Think of it as a universal translator at the UN. You speak SQL, and the connectors translate to every database in the room. The data never moves. The connectors are open source on GitHub under oslabs/os-athena-query-federation, so you can even build your own. Here's a real Nexer retail example. We want every pending order right now joined with that customer's historical segment and lifetime order value. The real-time data is in DynamoDB. The history is in S3 Parquet registered in the Glue catalog. Look at the FROM clause. We reference DynamoDB as a catalog prefix. That's the Lambda connector at work. We reference the Amazon Web Services data catalog prefix for the historical Parquet table. 1 SQL statement, 2 data sources, 0 ETL pipelines. One caveat though. The Lambda connectors do have cold starts and you pay for Lambda invocations. They're powerful but not free. Test your specific schema before depending on them in production. A quick but important distinction because the exam likes to trick you here. On the left, a plain Athena view is just a saved SQL statement stored in the Glue catalog. Think of it as a saved Amazon search. Every time you open it, the catalog runs the query fresh. Nothing is stored. Zero storage cost, always fresh, but you pay the full scan cost every time. On the right, and this is the part people miss, Athena does not natively create materialized views. If you want pre-computed, cached results, the Athena native answer is CTAS, create table as select, which writes the query output to S3 as Parquet. You then query that smaller table, which is way cheaper on repeats, but you pay S3 storage and the data is stale until you rerun the CTAS. The only materialized views Athena can read are ones built externally by EMR or Glue Spark and registered in the Glue catalog as iceberg tables. So remember, regular view equals always fresh, full scan. CTAS equals stored fast, but you manage the refresh. Last variant, Athena for Apache Spark. Amazon Web Services added a Jupyter-style notebook experience inside the Athena console where you can write PySpark code on a serverless Spark engine. So when do you pick which? Athena SQL is a calculator, fast for arithmetic on tables, declarative, priced per terabyte scanned. Athena Spark notebooks are a programmable scientific calculator, slower to set up, but you can write functions, loops, machine learning code, and use the full Python ecosystem. The pricing is different too. Athena Spark bills per DPU-hour, not per byte scanned. Default rule, pick Athena SQL only reach for Spark notebooks when you genuinely need imperative Python, machine learning libraries, or logic that SQL can't express. Don't pick Spark when SQL would suffice. It's extra cost and complexity. 5 mistakes that destroy Athena cost optimization in practice. First, select star on a Parquet table. You just paid for columnar storage and threw away the advantage. Always select only the columns you need. Second, partitioning on a high cardinality column like user_ID, you'll create millions of tiny folders and Athena will choke on S3 list operations. Third, the tiny files problem. Hundreds of small CSVs or JSON files under 128 megabytes each cause massive S3 overhead. Use CTAS or Glue to compact them into larger Parquet files, targeting 128 megabytes to 1 gigabyte each. Fourth, no BytesScannedCutoffPerQuery on any workgroup. One runaway query can scan a petabyte and produce a 5-figure bill. And fifth, forgetting that every query writes its results to S3. That results bucket quietly grows to terabytes over months. Set a 30 to 90 day lifecycle policy on it as standard hygiene. Tattoo this table to your brain before exam day. Avoid running MSCK REPAIR TABLE, that's Partition Projection. Cheapest way to convert CSV to Parquet, that's CTAS, not Glue, not EMR. Isolate teams and cap query cost, that's Workgroups plus BytesScannedCutoffPerQuery. Join DynamoDB and RDS without ETL, that's Athena Federated Query with Lambda connectors. And the biggest single Athena cost win, convert to Parquet with Snappy and partitions. If you internalize these 5 trigger phrases, you'll handle nearly every Athena question on the exam without thinking twice. 7 things to lock in before exam day. Athena is serverless SQL on S3, priced at $5 per terabyte scanned, and every optimization is just shrinking bytes. The Glue data catalog is Athena's metastore. Shared with Redshift Spectrum and EMR Partition Projection is the #1 Athena concept on the exam, and it kills MSCK REPAIR forever. CTAS is the cheapest CSV to Parquet conversion, with no Glue or EMR needed. Workgroups isolate teams, and BytesScannedCutoffPerQuery is your cost guardrail. Federated Query uses Lambda connectors to join DynamoDB, RDS, and Redshift with no data movement. And views equals 0 storage and always fresh, while materialized views are stored and can go stale. Now let's see how well you absorbed all of this with a quick 5-question quiz. All right, time to put your knowledge to the test. Question 1. A data engineering team has a table partitioned by date in S3 with over 50,000 daily partitions accumulated over 4 years. Running MSCK REPAIR table takes over an hour every time new data lands. What's the most effective fix? Is it A, switch the table to CSV format to reduce metadata overhead? B, configure partition projection in the table properties to compute partitions at query time? C, move the data to Redshift and stop using Athena? Or D, run a Glue crawler every hour instead of MSCK REPAIR? Take a moment to think about it. The answer is B. Partition projection stores the partition formula in table properties, so Athena calculates partition locations at query time, eliminating MSCK REPAIR table entirely. Any exam question describing slow partition maintenance on a high cardinality table points directly at partition projection. Question 2. Nexar Retail has 5 terabytes of raw CSV clickstream data in S3 that analysts query daily. The data engineering team needs the cheapest way to convert it to a query-optimized format. No existing Spark cluster, no Glue jobs. What should they do? Is it A, spin up an EMR cluster with Spark to read CSV and write Parquet? B, build a Glue ETL job using dynamic frames to repartition the data? C, run a single CTAS statement in Athena specifying format equals Parquet and Parquet underscore compression equals snappy? Or D, use Oz datasync to replicate the data to a new bucket in Parquet format? Take a moment to think about it. The answer is C, CTAS, create table as select, is the cheapest in-place conversion of S3 data because it uses Athena's existing serverless engine. No EMR cluster to spin up, no Glue job to author. Just one SQL statement that reads CSV and writes Parquet with snappy compression. Question 3. A company runs Athena across 3 departments: finance, marketing, and data science. Recently, a junior analyst accidentally ran select star on a 100 terabyte log table, costing $500. Leadership wants to prevent this from ever happening again while keeping each team's query history separate. What's the right solution? Is it A, create separate Athena workgroups per team, each with BytesScannedCutoffPerQuery set to an appropriate limit? B, add an IAM policy denying select star statements across the account? C, move Athena queries to Redshift serverless with usage limits? Or D, enable AWS budgets alerts on the Athena service? Take a moment to think about it. The answer is A. Workgroups provide team isolation with separate query histories, results buckets, and encryption settings. BytesScannedCutoffPerQuery is a hard per query limit that cancels any query exceeding the threshold before it runs. AWS budgets alerts only fire after costs are incurred, so they can't prevent the runaway query in the first place. Question 4. An analyst needs to run a single SQL query that joins real-time order status from DynamoDB with historical order history from S3 Parquet and customer profiles from RDS Postgres, without building any ETL pipeline. Which Athena feature solves this? Is it A, Athena materialized views with cross-source refresh? B, Athena for Apache Spark notebooks with PySpark connectors? C, Athena Federated query using Lambda-based data source connectors? Or D, Glue data catalog cross-region replication? Take a moment to think about it. The answer is C, Athena Federated query deploys Lambda-based connectors to translate Athena SQL into each source system's native query language. The data never moves. The connectors push filters down and stream results back into a single query result. Exactly the cross-source join scenario described. Last question. A data engineer wants Athena, Redshift Spectrum, and EMR to all query the same tables using a single shared schema definition. Which service stores that shared metadata? Is it A, Amazon S3 bucket tags? B, Amazon DynamoDB metastore tables? C, AWS Glue data catalog? Or D, AWS Systems Manager parameter store? Take a moment to think about it. The answer is C, the AWS Glue data catalog is the unified metastore that Athena, Redshift Spectrum, and EMR all share. One table definition in the Glue catalog is immediately queryable from any of those engines. This shared catalog is exactly why Athena integrates so cleanly with the rest of the AWS analytics stack. And that's a wrap on Amazon Athena, serverless querying and cost optimization. If this helped you out, smash that like button and subscribe for more. See you in the next one.